Bismillahirrahmanirrahim. Hi, and welcome to this concise, highly productive course on the Julia programming language. I'm Dr. Nauman. I have a PhD and a postdoc in applications of machine learning. I have more than 15 years of teaching experience and several bestseller courses online, including many related to machine learning and data science. I know where people struggle with these courses since I've guided several thousand students in these areas. Data science and machine learning are fast-paced fields where you need to keep up with the latest trends. If you get stuck with old tools, languages, or frameworks currently in use in your job, you will have trouble when you try to switch jobs or try to solve new problems. This is why you need to keep yourself updated with the latest tools and languages coming out in this field. In data science and machine learning, the hot new language that shows a lot of promise is the Julia programming language. Julia has been gaining acceptance in the industry very fast. Many people feel that it has the best of both worlds. It's very, very fast. It's comparable to fastest languages such as C, and it's also extremely easy to learn. And that's because its basic syntax is very similar to the popular Python language. Due to these two strengths, many feel that it will quickly become the language of choice, or at least a significant player in the fields of scientific computing, data science, and machine learning very soon. In this course, you will learn the best features of Julia in the smallest amount of time possible. We take a concise approach towards learning that will allow you to learn the basic syntax of Julia, how it's different from Python, how to apply it to the concepts of data science, and last but not least, how its machine learning capabilities can enable you to supercharge your ML career. If you know Julia, you will stand out from everyone else who has worked with data science or machine learning. Simply a mention of Julia in your profile will show potential employers that you are staying ahead of everyone else and know the state of the art. Knowing Julia would also allow you to work with the latest and greatest data science tools and machine learning models and also create your own very, very easily. And the best part is that there are no prerequisites to taking this course. If you know some basic Python, it will definitely help, but you will still get all of the content if you've never worked with Python before. I will, however, assume that you've worked with some basic data science and machine learning models before, since we won't cover the machine learning theory in this course. But if you have worked with any data science tools and or machine learning models before, you should have no trouble following the content. This is aimed to be a first course in Julia. It will give you the foundations you need to keep learning on your own even after the course. Take a look at the preview videos to see what kind of lectures to expect. Everything is practical, no boring slides. Very concise and will get you up to speed in no time at all. And I provide stunning support. All questions are answered within 24 hours. All this coupled with a 30-day no questions asked money back guarantee means you have nothing to lose. So enroll now and I'll see you on the inside. Hi, welcome to the course and thanks for joining. Before we start, we obviously need to set Julia up for our system. It's fairly straightforward, but I'm going to go through this just in case so that you can follow along. So we'll set Julia up for Windows, Linux, and macOS, and you can follow along depending on your own operating system. So let's start off with Windows. To get Julia, head over to julialang.org/downloads. I would recommend that you install the current stable release, which is currently at 1.6.0. Julia releases come out very frequently, so this might be different depending on when you're viewing this course. In any case, go ahead and download the Windows 64-bit installer. This is an executable file, which you can go ahead and simply right-click and run, and it will set up the installer for you. So the only thing that you should be doing over here is changing the installation directory to something simpler like c:/Julia 160 or whatever you feel like. So something simple. Okay. Hit next. This is going to show you some options and just keep hitting next and it'll set it up for you. So it's fairly straightforward. So we wait for just a minute while it sets it up. When it's done, simply click on finish and then you can head over to c:/Julia 160 or wherever you set it up. In the bin directory, there is going to be an executable called Julia. You can simply go ahead and run that and it will show you the Julia prompt that you can see over here. So that's the only platform specific stuff that you need to do for Windows. Let's head over to the installation on Linux and then Mac, and then we'll come back to what you need to do over here. So if you're on Linux, you can simply go ahead and download the current stable release version 1.6.0 for your Linux distribution. So typically this is going to be a 64-bit installation on the x86. You can also download the ARM-based compressed file if you have your Linux set up on an ARM machine. You simply go ahead and download this and then extract the file. Your file name might be different depending on the version that you have or the architecture, but you just need to extract this file. cd into the newly created directory, and then say bin/Julia. This is going to execute the Julia interpreter for you, and you will arrive at the same prompt as you did for Windows. Similarly, if you're on the Mac, you can go ahead and download the MacOS X DMG file. This is fairly straightforward. You just click on this and it's going to set it up for you. There are a couple of things that you have to do for Mac. So you can click on this help link and it will show you the two commands that you need to do to add Julia to the path. So you can say rm-f/usr local bin Julia and then create a symbolic link using this command. So you would need to obviously set up the correct directory over here. That's all there is to it. Once you have that, you can go ahead to your terminal in your Mac environment and simply say Julia and you will arrive at the terminal. So irrespective of which platform you're working on, which operating system you have, you will arrive at a Julia prompt over here with which we can start working. So in the next video, we are going to take a look at how we can set up the rest of the environment on any of these operating systems and then start working with Julia code. Now that we've set up our environment, we can go ahead and start working with the actual language. We'll take a look at the basics of the language and then move on to the more advanced topics. You can follow the tutorial by typing all this stuff on your own in a new notebook, or you can follow along using the notebooks that are provided with this course. So let's start off with the basic definition of a variable. So we can go ahead and say awesome variable is equal to 25. So that defines a variable. As you can see, the variables are dynamically typed, so you don't need to define their types, but they do have a type, and we'll take a look at that in a minute. You can take a look at the value of the variable using just awesome_var, so that gives you 25. Now, one important thing that immediately differentiates Julia from almost any other programming language is that variable names themselves can be in Unicode in Julia. For instance, in Python, you can define any variable x to hold a string which has Unicode in it. Right? So we're using a Unicode emoji in this case, but the variable name itself in Python cannot be a Unicode, right? So here it's very possible to do this. So let's go ahead and run this. So as you can see, this is just a variable which holds this string. And if you try to output the value of this variable, it works perfectly fine, right? So this seems weird. And the way to type this is to go ahead and say /:smi and hit tab. That is going to give you a pop-up and you can select whichever smiley you want. So for instance, if you need this, you hit enter and then you hit tab again, right? So enter. It seems weird, but you're almost never going to use smileys in your notebooks, right? So that's weird. But in general, Julia does use Unicode variables. For instance, over here we have sigma, and if you want to type sigma, you can say /sigma and hit tab and it's going to turn it into the sigma letter. And because Julia aims to translate mathematical models into code while remaining visually similar, this is very helpful, right? So for instance, if you have a mathematical formula that says sigma is equal to 2.5, you can write that exactly like sigma is equal to 2.5 instead of having to say s is equal to 2.5 or having to write sigma in full. So it's really useful, and it's the general practice in Julia ecosystem to actually use Unicode variable names. Okay, so we'll come back to this again and again. So forget about this for a minute. This is how you type it. I'll cover this again. So /:smi, and then here you hit tab, you get a drop down, you hit enter, that completes it, and then hit tab again and enter, and that inputs it. It seems like a lot of work for emojis, but you're not going to do emojis in code. The Latin and Greek symbols, they're really easy. So you say /sigma, hit tab, and you're done. Okay. Anyway, so we have defined this variable name over here. And if you want to take a look at its type, we can say type of this cat. It's a string. Now, two things to notice over here. One is that this variable is just a variable. It's just a name of the variable. It happens to be an emoji. The other thing is that all variables have a type. Always they are going to have a type, and Julia is somewhere in the middle of Python and C++. It is going to have very strong types, and types have hierarchies in between them, but you don't have to explicitly specify them unless you're doing optimization of the code. Okay, we'll come back to this when we get to machine learning part. You can say type of this A, and this is a character. Now notice the difference between double quotes and single quotes in Julia. In Julia, strings are defined using double quotes, and single quotes are used for single characters, just like C. Okay. Type of double quotes A is a string. We can define sigma is equal to 2.5 as we just discussed. And now you can go ahead and pass this to a function. For instance, we have a square root function. We can say the square root of sigma squared is equal to obviously 2.5. Another thing to note over here is that Julia uses the caret symbol or this little hat symbol for exponentiation. So sigma squared is using cat and not two sterics, as is with other languages. We can print using the println function. So this is also a built-in. You can say sigma is equal to sigma and you get the value out. So this is println for printing a line. So it's /n terminated. Okay. If you need help with any built-in or another function, you can say question mark space function name and you'll get a detailed help regarding that. Okay. So it's giving you some examples and all the things that you can do with it. We also have integers. So an integer by default is int64. We also have 32-bit integers. We'll come to that when we do type conversions. We also have real numbers. So those go into float 64 or float 32 depending on the system configuration. You can do multiple assignments. So I understand that I'm going a little quickly, but hopefully this will be very clear for you, but because this is really basic stuff. If you have any questions, please do feel free to ask questions. So we can have a comma b is equal to 10 comma 20. 10 goes into a and 20 goes into b. Okay. We also have another data type, which is the literal type. So you can say :4, and this is going to be an int64 because :4 is the same as 4. :b is the same as b, and that is not a string, that is not a character, that is what is called a symbol, right? So if you try to print this out, if you say println b, it's going to print some other weird stuff, right? So this is not the ASCII b, this is not the string b, not Unicode b, it's just a symbol which you can use. It has specific certain purposes that we'll get to when we try to apply these concepts. Just take note of this syntax that you can have a colon and then a string of characters. So you can say best and that will be a symbol, and you cannot say best is equal to 34, right? So that is an error. So best itself is not a variable, it's an actual value. Okay, hope that makes sense. Just as 4, the digit 4 is a literal type, best is now a literal type as well. Okay, let's go ahead and do some basic arithmetic. So we can do println. We have addition, subtraction, multiplication, division, and modulus. So they do what you would expect them to do. So 3 plus 5 is 8, 3 minus 1 is 2, 3 into 4 is 12. Because we don't have any spaces in between them, we have to put spaces like that to differentiate them. Okay, so println does not insert spaces in between different characters as print does in Python. Okay. We can output strings, so there is no gap in between these two things. We can pass it a list. So a list in Julia is just like it is in Python. So comma separated square brackets, and that is going to output this over here. Notice one very important thing over here. 3 plus 5, they are both integers, and when you add them together, you get an integer out. But this is saying 8.0. The reason for that is the lists that you create in Julia are going to be typed. The type of the whole list is going to be a particular type. Julia does what is called type promotion. So if you have any float in the list, everything is going to be converted into a float. So this 3 by 5 leads to 0.6, which is a float. And because of that, the whole list is converted into a float. An easier example for that is 1, 2, 4.0. And the type of this is going to be an array, which is what Julia calls lists. And in the array, the type of values for all the elements is float 64, and it's a one-dimensional array, right? So it's one-dimensional, as you can see, and the data type of all the elements is float 64. That is how Julia works. It gives a specific type to a list, and the reason for that is it improves the performance by a lot. Okay, just something to keep in mind. Print does the same thing as println, except it does not output a new line at the end. 4 divided by 2 over here is an integer division. So 3 by 5 is an integer division that results in 0.6, but 4/2 is actually a fraction. So this is a rational which is built into Julia. So 4 by 2 is the fraction 2 by 1. You can actually add fractions and get results in actual fractions output, right? So this is not going to be any precision loss because this is actual irrational number, and you have built-in support for rationals in Julia. We can go ahead and convert the data types among each other. So I can convert an integer to an integer 64. So 1 goes into that. I can convert it into a float 64. So 1.0. I can convert 1.3 into an integer 64, and that is going to give me an error because this 0.3 cannot be discarded. You'll either have to seal it first or round it first and then go ahead and convert it. Okay. So that is the basic conversion. We do have to do a lot of different conversion things that we'll get to later on in the course. We have Boolean operators. So we have two values over here. Val t is true, val f is false, and is using two ampersand signs. So true and false is false, or is using two pipe symbols, and not is using the exclamation mark. So basic stuff. We also have string operations. So we have name John over here and the age over here. We can output them using interpolation. So wherever you have dollar and brackets in your string, they are going to be interpolated, and this variable name is going to be inserted over here. So the customer's name is John, who is 35 years old, right? So that is called string interpolation. It's very useful. We also have string concatenation. So concatenation typically is done using plus, but here it's using the multiply operator. There is a reason for that. We don't want to get into that, but this is a conscious decision to use steric instead of plus. So that does the concatenation. You can also join multiple strings using the join function. So this is a built-in function, and you can give it a list of strings and a delimiter, right? So it's going to join s1 space s2 space and so on, right? So s1 space s2, and it's going to return a string to you. You can put the list outside and give it to join, and this works as well. We've already seen string repetition. So we use, instead of multiply, we use the caret or the hat operator, right? So you can go ahead and do that. So this repeats the string 3 times. So this is the basic data types that we have, and we're going to obviously use them in detail later on in the course. But just to give you a pro tip, if you're working in the notebook, you can right click and click on new console for notebook. This gives you a console over here, which is based on this notebook. You can drag it out over here to the side, and now you can do all the experimentation over here. So you can say 4, and this is going to go away after you close the console. So you don't have to mess up your notebook over here. So this is really good for experimentation and just taking a look at what's going on, right? So let's get rid of this. In the next video, we are going to take a look at how these variables can be combined using control structures such as conditionals and loop. If you worked with Python, you would already be very familiar with dictionaries. They're very common, very prevalent in Python. If you come from Java or C, C++, C Sharp, they are called maps or hash maps or any type of map. Okay, so they are a collection of key value pairs. So for instance, let's start off with the syntax. So you say D is equal to dict, and then you can define the keys and the values, which are separated by the arrow operator. So key arrow value, comma, key arrow value, and so on. You can have multiple values. You can have multiple key value pairs in this one dictionary. Okay. There is no shorthand for dictionary in Julia as there is for arrays. So you just have to define it using the dict keyword. Okay. So you do that, D is equal to dict. So you have this dictionary over here in which we have strings as keys and strings as values. It has 2 entries. You can see. You can access it as usual using the square brackets. So you can say D language. D dot language does not work. It does in some languages, but it doesn't in Julia. You can change the value or even add new values. You can say D explorer is equal to perseverance, and that is going to change D. So you can have that. You can modify this or mutate the object using the pop bang operator. So pop bang, from the previous video, you would recall that bang means it's going to modify D. So if you say pop D, this is going to return the final value that you have over here, which we just added over here, and it's going to remove it from the dictionary as well. So that has been removed from the dictionary. Okay. You can merge 2 dictionaries together. So if you have D, which is this guy over here, and you have another dictionary E in which you have OS and language. So we have language both in this and in this. If you try to merge them together, again, merge is with a bang, which means it's going to modify D. So by convention, this D is going to be modified and E is going to remain the same. So what it does is it takes D and then goes through E and inserts all the values into D from E. So E is the source, D is the destination. Anything that is in both is going to be taken from E. Okay. So it makes a lot more sense if you just take a look at the example. So if you merge D and E, the language is now Java because Java was in E, and E essentially overrides everything that is in D. Okay. So if you show D, you can see that language has been replaced with that. If you show E, that is unmodified, that remains the same. Okay, so merge is going to modify D, take everything from E and throw it at D. If D already had that key before, it's going to be overridden. Okay, you can loop over the values of the dictionary using for k comma v in D, and you can output them using string interpolation. So you can say key is equal to $k, tab character value is equal to $v, and this is going to output all of that for you. Okay, you can also use symbols as keys in dictionary. So you can say sample is equal to dict :lang is Julia and ID is Pluto. So now you can access them using symbols just as you could with strings. So now here the keys are symbols instead of strings. So you can say simple lang and you get the value out. Okay, rest of it is exactly the same. So you can say for k comma v in simple and you print it out, you get lang and ID out, right? So those are the basics of the dictionary. Obviously, there is a lot to do with dictionaries, but we don't want to cover them here. This is the basic syntax that you need. That is all there is to it. Once we start using them in the real world, you'll get a lot more practice with it. For now, let's go back to the arrays and take a look at the specific functionality that Julia provides for arrays that makes Julia special. So let's do that in the next video. As you know, one of the most important areas in which Julia really shines is numerical computing and machine learning. The reason for this is the excellent built-in support for arrays, matrices, and tensors in Julia. So let's go ahead and take a look at that. So we're going to define a list as we did before, and these are called arrays in Julia. So if we do that, we'll get an array of type string, which is one-dimensional, and it has 3 elements. We can take a look at the type of this variable to see that it is indeed an array which holds all elements of type string, and it is one-dimensional. So this is a 1D array of string values. Okay. Similarly, we can define a 1D array of integer values. So this is going to be an int64 type array with one dimension only, right? We can go ahead and do usual operations on that, such as push, which pushes the element at the end, and we can pop, which is going to remove the element and modify the actual array, right? So let's go ahead and turn this into a 2D array. So we can do that using the usual syntax of a list of lists. So this is a list, and in it, each element in itself is a list, right? So let's go ahead and do that. This is going to give us an array, and the type of each element in that array is an array itself, right? So that is how you read this. It's a 3-element array, and each element itself is an array of integers. So this one guy over here is this array of integers, which is one-dimensional. Okay, you can take a look at the type, which gives you the same information. Now notice that this is not a 2D matrix. This is an array of arrays, which means that I can go ahead and change the size of this to that, and this still works, right? So the size of each array can be different because the type is still int64, 1. Okay, so what if we want to create a 2D matrix or a 2D array instead of an array of arrays? The syntax for that is slightly different but very similar. So we say x is equal to 1, 2, 3. Notice that there are no commas in between each element. So here we have commas, and here there are no commas. So x is equal to 1, 2, 3, and you will notice that the type now is 1x3 array. So it's a 1 into 3 array, and each element is int64, and the dimensions of this array are 2 now, right? So notice the difference of this. This is extremely important, that the type of this is an array of arrays, and this is a 2D array, and the size is 1 cross 3. Okay, so this is a pure 1D array. Now we can go ahead and transpose this, and this is going to turn this into a column vector, so to say, and you will see that the type is something really weird, but it's still an array of int64s, which is 2-dimensional, and it has been converted somehow into another data type, but we don't want to go into that just now. We'll come back to this when we need it. Okay, we can take this step further and do a 2D array. So we can have 1, 2, 3, 4, 5, 6, 7, 8, 9. And notice that we are missing the commas in between the different rows as well. right? So no commas at all. That is going to convert this into a matrix or a 2D array of int64 types, right? So this is a 3 by 3 array. What that means is if I try to do this, this is not going to work. So if I say 7, 8, 9, 12, the number of columns of each array must match, right? So that has to be equal for all of them. That is how a matrix works. Okay, so let's go ahead and change that back. So this is now a matrix which is a 2D array, each element of which is int64. If you convert one of these to a float, everything is going to turn into a float. So now this is a float 64 array. All the elements are now floats. Okay, we've done this before. Now let's go ahead and take a look at the shapes of arrays and a little bit about reshaping, how that works, because this is going to be very important later on when we do machine learning with Julia. So we can say size of mat, and this is going to tell us in tuple that this is a 3 by 3 matrix. We can also go ahead and take a look at the size of this X that we created, which was essentially a vector. So this is a 1 by 3, and we can say the size of fib, which is this guy over here. So fib is an array which has 7 elements, right? So you will notice the difference. This is not 1 cross 7, this is just 7. Okay, because this is a one-dimensional array and that has just this one dimension which has 7 elements. Here we have a still one-dimensional array, but it's a 1 cross 3 matrix, or what we term typically as a vector. So this has slight distinction, and when you do machine learning, this is going to cause headaches or really make your life easy if you understand this. Okay, so go ahead and revise this so that you understand the difference between the two. Okay, so let's define a matrix X which has these elements. We can go ahead and reshape this. So this is right now a 4 by 3 array, so 4 rows and 3 columns. We can go ahead and reshape this into a 2 by 6 matrix, right? So we can reshape this. So you will notice this goes 1 4, then 7 10, then 2 5, then 8 11, 3 6, and 9 12, right? So that is how the reshaping works. It's going to convert the 4 by 3 array into a 2 by 6 array according to this rule. It goes from left top to bottom and then to the right, right? So that is how it goes. We can reshape this to a 12 by 1. So it goes 1 4 7, 10 2 5 8 11, 3 6 9 12, right? So that is how this goes. So top left, first it goes down, then it goes right, and then down, and then right, and then down. That is how reshaping works. Okay, we can go ahead and reshape back to a 4 by 3, and the way these rules work is if you change something and then you reshape it back, the rules are simply going to work out to produce the same matrix for you. So if you reshape this into a 4 by 3, it's going to create the first column as 1 4 7 10, then the second column as 2 5 8 11, and the last column as 3 6 9 12, which is exactly the same thing that we started with over here. Okay, so the shaping really works out. So why is this reshaping necessary? Sometimes when you have a model that expects a specific shape and you have your data in another shape, you don't want to modify the model, you want to modify your data to fit the shape, right? So again, when we get to the machine learning part, we'll see how this works out. Right now, we're just doing the building blocks. So finally, let's go ahead and take a look at some helper functions for working with matrices. So we have a rand function, which creates a 4 by 3 array or a matrix which has random numbers going from 0 all the way up to 1. Okay, so each element is uniformly distributed from 0 to 1. Okay, we can save this in an array. So over here, mat, we can create a copy of that. And if you recall from the last lecture, if we modify mat to 1 comma 1, so that is essentially how you access the individual elements within the matrix. So row comma column, if you change that, mat2 is changed, and so is mat1, right? So you would recall this is the same problem of sharing the memory even though you did this, right? So you did not create a copy, you simply created a new reference variable which is pointing to the same matrix. If you want to actually create a copy, which is sometimes necessary, you can go ahead and use the copy function as before. So if you do that, mat311 changes mat3 but does not change mat itself. Okay, so mat remains the same as before and mat3 can now change. So you can use copy if you want to create an actual copy of your whole data. Obviously, if you have like a million by million matrix, you don't want to create a copy, you want to somehow optimize your code. Anyway, just as with all other modern languages, we have a way of creating lists or arrays using comprehensions, which are a shortcut for creating lists. So if you have not seen this before, it's a very simple syntax. So we can say for I in 1 to 5. So this is going to create a list which is going to go from 1 to 5, and for each of the elements it's going to collect this. It's a lot more difficult to explain. It's very easy to just show it to you, so I'll show that to you. So it creates a 5 element array. It goes from 1 to 5 and it creates I, the second time I, and the third time I, and the fourth time I, and the fifth time I, right? So you can go ahead and change this to I square, and this is going to create this list for you. You can go all the way up to 10, and this is going to go all the way up to 10 and square the numbers. Okay, so that is how this works. You can also go ahead and do a nested loop. So for I in 1 to 5, comma, j in 6 to 10. So this is essentially going to create a nested loop in which I is going to go from 1 to 5, and within that loop, j is going to go from 6 to 10. So essentially when you do I comma j, the first time it's going to be 1 comma 6, then it's going to be 1 comma 7, then 1 comma 8, all the way up to 1 comma 10. Then it's going to go 2 comma 6, 2 comma 7, all the way up to 2 comma 10, and so on. Right? So this creates a 5 by 5 array because these are 5 elements and these are 5. And the first time it's going to go 1 6, 1 7, 1 8, 1 9, 1 10. And the second time when the outer loop runs, it does this. Right? So this is going to be a Cartesian product. It's a very handy way of doing simple manipulations to create matrices. Obviously, this is right now a 5 by 5 array in which each element is a tuple. And within that tuple, we have int64, int64 values, right? So int64, one element is an array and the array itself is 5 by 5. So I'll repeat that. Make sure that you understand this. We are slowly building the type system of Julia. We're building an understanding of this type system so that when you see very large complicated data types, you understand them well, right? So once again, this is a 5 by 5 array because this is a 5 by 5 matrix. Each element itself is a tuple. So this is that tuple. The array itself is two-dimensional because it has rows and it has columns. And within the tuple, there are two elements. The first one is an int64 and the second one is also an int64. Okay. As before, we can go ahead and change each individual element to be something else. So this can be I square comma j. So same thing, but this is going to go from 1, then 4, 9, 16, 25. We can also say j plus 1 or whatever function you want to use, right? So 7, 8, 9, 10, 11. You can also do by 2. So all of this works out, right? So you can have fractions. So now you have a 5 by 5 array in which each element is a tuple. The first element of that tuple is an int64 and the second is a rational of int64s, right? So now this is getting really complicated. Make sure that you pause and you understand this. Okay. Finally, a couple of operations. So you can have a random array created which is 3 by 3, but instead of from 0 to 1, each element is going to be between 10 and 20. Okay. So you have these int64s and these are between 10 and 20, both inclusive. Okay. You can also convert them to floats by just setting this 10 to a 10 dot. So 10 dot is going to mean start from the float 10, go all the way up to 20. And the type promotion system in Julia is going to convert everything into floats. So this is an array of int64s and this is an array of float 64s. Okay. Instead of random values, we can provide a specific value using the fill method. So we can create a fill method in which we are going to have a 3-sized array and it's going to have the exact value 10, right? So x is going to have 3 tens over here. Okay. Now that we have this a and this x, we can go ahead and multiply them together. And the syntax, because this is built in Julia, you can simply say a into x and this is just going to work out perfectly, right? So this is obviously a matrix vector multiplication. So you have the typical rule of row multiplied by this vector and the second row multiplied by this vector and the third row multiplied by this vector to give you the final result out, right? So this works really well. We can also do basic operations like transpose. So you can say a prime to get the transpose. So this goes from 10, 15, 12 to 10, 15, 12. So rows into columns, columns into rows. That's the transpose. You can also do a prime into a. And because this is a very common operation, Julia provides a shortcut. So you can even omit the multiply sign. You can say a prime a, and this is going to do the same operation. So this is very typical with Julia. Julia strives to make sure that its syntax matches the actual mathematics as closely as possible, because that helps people translate research papers and research work which is in mathematics into Julia code, right? So your Julia code is going to look very similar to the actual mathematics that is in research papers and in the state-of-the-art work. Okay. You can do the trace. So trace of A is, well, trace is not defined because we need to do linear algebra for that. So we have the package using linear algebra. So recall that if this package gives you an error, you can do pkg.add linear algebra as we did in the very first video of this course. Okay. So now you can do trace of A. You can calculate the determinant very easily using the det function, and you can calculate the inverse, obviously, if it's possible, to create the inverse. Okay. You can solve linear equations directly. So for instance, you have A, which is a random variable. You have an X, which we already have. You can say B is equal to A into X. So that creates the B. And if you recall, if you have this A into X is equal to B, you can calculate the actual values and solve for B, right? So you can say A by B and it gives you the actual values. Okay. So as you can see, it's very close. And this isn't exactly 10.0 because of floating point arithmetic in computers, but this works out really well, right? So you get the X back out. If you don't understand this linear equations, if you don't remember your linear algebra, it's fine. You don't really need it for this course or even for machine learning, but I just wanted to cover it to let you know that this is available in Julia, right? Finally, we've seen a two-dimensional array, but you can go ahead and convert these into tensors, which are larger dimensional matrices, so to say. So you can have a row, comma, column, comma, depth, comma, something else, right? So you can have a four-dimensional array as well. So now this is a 4 into 3 into 2 array. So these are now 3 dimensions, which you can think that this is one array, and coming out from the screen is this other piece of paper. So think of these as two different pieces of paper lying on top of each other. So on the first paper, this is written, and on the second paper, this is written. So this is now kind of like a 3-dimensional structure. So instead of a 2-dimensional structure, which can be written on a paper, now you have a 3-dimensional structure. So this is called a tensor, where the name TensorFlow comes from, by the way. So these are tensors. If you're not familiar with tensors, we'll get to these when you get to machine learning. But for now, it's sufficient to say that you can create any number of dimensions using this syntax, right? So now you have a 4 by 3 by 2 by 5 array, right? So 4-dimensional array. You can see a lot more in this over here. So in this linear algebra. So on this link, you have all the functionality that is provided with the linear algebra package in Julia. So this is built in, you don't have to install anything for this. So if you want to explore this further, you're welcome to go ahead. For our purposes, this is all we need. And when we start doing data manipulation and machine learning, we'll come back to this and go through this once more. In the next video, we are going to take a look at some final thoughts about different data types. Those data types aren't really used in machine learning and data science, but I'm including them here for the sake of completeness. We've already used functions in the previous videos. Now let's go ahead and define functions using the basic syntax. So the semantics of most of this stuff will be already clear to you, but we're going to see how Julia approaches this, right? So let's first define a basic function. So for that, you use the keyword function and you end the function body using the end keyword, right? So that's how Julia defines blocks. Within the function, you can have multiple lines. Indentation is not important, obviously, for blocks. One important difference to note over here is that we don't necessarily need a return statement over here. If we say x into x, this is going to be the last line that is going to be executed when this function is called. So this value of x into x is going to be automatically returned. You have the parameter x over here, and we can go ahead and call this function. So let's first define this. And then we can go ahead and call this using square 4, and this is going to return the value 16. So you don't need the return keyword over here, but it's still a good practice to include it just to make your code a little more readable, okay? It depends on who you ask. Some people prefer returns. Some people say it should be without the return. It depends on who you ask. But personally, I prefer to have a return statement over here, okay? So we have the square function. You will notice that we don't have a data type over here, so it's implicit. So if we have hello name and we simply print the value over here, we can go ahead and call hello with the string parameter. So it's going to print hello there world. We can also pass it an integer. So this is obviously going to work perfectly fine because name can hold any different data type. We can even create a matrix over here using rand function and pass that to hello, and that is still going to work. So anything will print as long as it can be converted into the string, right? So this works perfectly fine. So this is probably stuff that you're already familiar with. We're just looking at the syntax that Julia provides for this. But now we get to some of the stuff that is different in Julia. So for instance, you can define one-liner functions using this syntax of defining the function name and parameters in parentheses is equal to, and then the one line of function body that is going to return the value of the function, right? So it's much easier to just demonstrate this. So hover x is equal to x by 2. If you run that, you get a function back which is going to be called hover, and it's going to take one argument. So hover 5 is going to return obviously 5 by 2, which is a rational number. So this body is going to be returned to you. So this is very useful when you have one-liner functions, and it makes your code look very similar to mathematics, which, as we saw in the previous video, is one of the objectives of Julia syntax. Okay. Whenever we have functions which try to modify stuff, by convention, we append an exclamation mark to the function name. So we've seen this before. Let's go ahead and take a look at this again, just for the sake of completeness. So we have an array named v over here. We can go ahead and call this sort function on it. It's going to sort it, but you will notice that v remains the same. The reason for that is sort does not mutate the variable that you pass to it. Okay. However, there is a variation of sort which ends with a bang, and that is a mutating function, which means that if you pass v to this sort with a bang, it's going to actually modify v. So this is very pervasive in Julia. Whenever you have functions which end with a bang, they are going to mutate, or they may mutate your variables. Okay. So that should be fairly straightforward. Okay. We can also have overloaded methods. So this is slightly different from what you might be familiar with if you come from Python. This is very common in typed languages such as Java and C++ and C. So let's explain this using an example. So you have a function called showNumber, and it's going to print the value of the integer that you pass to it. Because I've just told you that this function is going to work on an integer, we can define the data type of the parameter as an integer 64, right? So a 64-bit integer. So the syntax for that is you say x : int 64. So that means that this x can only hold an integer 64 or int 64, right? 64-bit integer. If you try to pass it anything else, this is not going to work. So let's try and do that. So you define the function, you get the function back. You can call it using showNumber 65. This works perfectly well. But if you try to pass it a float, this is not going to work because a float is not an integer. So it cannot go into x because x has to be an int 64. Moreover, float cannot be promoted to an integer, right? So that's very important. If we had defined this x as a float and we had tried to pass it an integer, that would have worked because integers can be promoted to floats, but floats are higher up in the hierarchy than integers, so they cannot be converted into integers automatically. So if you try to do that, you'll get an error. And it's very prudent right now to take a look at the error. So the error says method error, no method matching showNumber : float. So what this says is you're trying to call a function which is called showNumber, and you're trying to pass a float to it, and there is no method that is available that accepts a float. No method named showNumber which accepts a float, right? So what we can do is we can go ahead and define such a function. So now we are going to define another showNumber, and in it we are going to have the same number of arguments, which is x, except this time the data type of x is going to be a float 64, right? So we can define this function, and now we can call showNumber with an integer and showNumber with a float as well. And you will notice that these are two completely different functions. So this body has nothing to do with this body, even though the names of both the functions are the same. Okay. So the first one is printing this and the second one is printing this, but they have the same name. The way this works in Julia is you have what are called functions. So showNumber is a function and it has two methods, right? So showNumber has two methods. For this generic function showNumber, one takes a float 64 and the other takes an int 64, right? So this is called function overloading. If you come from Java or C++ or C or any of the strictly typed languages, you would know what function overloading is. So this comes in very handy when you try to apply a function such as plus on different data types. So for instance, adding two matrices has different logic, adding two vectors has different logic, adding two complex numbers has different logic. So all of these logics you don't have to worry about. All you would do is call the plus function and the methods are going to be automatically matched by Julia. So the reason for doing this is this speeds up the performance of the different function calls because you can specify different logic for different types of data that you can have. And that makes the life of the compiler very easy, and that in turn means that your code is going to run much faster, right? So this is how internally Julia speeds things up, and this is very important, but it's slightly advanced topic, so we're not going to go more in the detail. I'll just show you the methods that are available for the generic function plus. So plus is simply a function, nothing important going on over here. So plus can work on two floats, it can work on two 16-bit floats, it can work on a complex boolean and a boolean, it can work with complex boolean and real, it can work even with two missing values, right? And there are a huge number of things that plus can do depending on the data type. And whenever you write plus, for instance 2 plus 4, one of these is going to be called, and there is a hierarchy going on. So if you have a function which does not have a particular method for a data type, a method in a higher level of the hierarchy can be called. So for the moment, that's all that you need to understand. When we get to more details of this, we're going to take a look at the specifics of how they are implemented in machine learning and data science when we get to that, right? So this is all you need to understand for the moment. So let's go ahead and take a look at some of the other concepts, such as default values. So let's again explain this using an example. So for instance, if you call log of 8, right? So by default in mathematics, whenever you say log, you mean natural log, right? So log to the base e. If you don't know what logs are, it's not really important. It's just a mathematical function that is very useful in a lot of things. But for the moment, all you need to understand is that this function actually has a hidden parameter in it, right? So log of 8 to the base of what? So that what by default is e, right? So the mathematical constant e. But you can change that. For instance, in computer science, we are usually concerned with log to the base 2. So you can call log of the same number 8, but to the base 2, and this is going to give you 3 back, right? So essentially, if you raise 2 to the 3, you get 8. If you raise e to the 2.07, you get 8, right? So that's how log works. So what we're trying to do over here is understand how this works, that the same function can work on different number of parameters. In the previous example, we saw how you can have a method for different data types. And here we are taking a look at different methods for different number of parameters. Okay, so that is how this works. These are called default values. So for that, let's take an example that we are going to pass a collection or a sequence of numbers to this collection log function, and it's going to calculate the log for all of these numbers, right? So the syntax is fairly straightforward. You're going to pass it a collection and you're going to pass it a base, and that base by default is going to be 2, right? You can call log base I for I in collection. So for all of the values that are passed to it, you calculate the log to the base I, right? So let's run this. So we have a function, we can call this, we can say collection log 4, 8, 16 and to the base 10. So this is going to return 0.6, 0.9 and 1.4. We can go ahead and omit the base, and this is going to now use the default value of 2. So if you've come from Python, you would be familiar with these default values, but in Julia there are slight differences, and that is what we're going to take a look at now. For instance, if you have base is equal to 2 over here, you cannot have a parameter that does not have a default value coming after it, right? So all the parameters which have a default value have to go at the end, right? So you have to change collection comma base is equal to 2 as we defined over here. You cannot have them the other way around. If you try to do that, you're going to get an error. So optional positional arguments must occur at end, right? So it's fairly straightforward. However, if you do need optional parameters at the beginning, you can separate your positional arguments and your keyword based arguments. So you can have base is equal to 2. This is going to be a positional argument and this is going to be a keyword based argument. So you can call this. This works perfectly fine. Notice the difference. Here we have a comma, here we have a semicolon. So these are now two different types. These are going to be positional, so you can pass them without having to refer to their name. But this collection over here now has to be passed using its name, right? So if you try to do this, this is going to give you an error. It says keyword argument collection is not assigned. You might be expecting that base is equal to 2 is default. So base is going to take on the value 2 and the only argument that I'm passing over here would go in collection. But that's not how Julia works. The way this works is anything after the semicolon has to be explicitly specified. So you have to say collection is equal to 4, 8, 16 and now this is going to work perfectly fine. You can also pass 10 over here. So this is going to go into base. So everything works out perfectly well. I personally would not recommend that you try to do this in your own code, but I've covered this here because you are going to see other people's code which is going to use this syntax. So you should be aware of this minor inconvenience of going from one language to another. So that's all you need to understand for now. As before, once we've covered all the syntax, we are going to take a look at applications of this in data science and machine learning, and this will become a lot more clear. Okay, so in the next video, we are going to take a look at another type of functions which are very pervasive in Julia, and you might not have worked with them before. Even if you have, we have to take a look at how Julia approaches them. So let's take a look at that in the next video. You've now seen all the core syntax of Julia language. There are a couple of things left, but we'll get to them when we need them. So now we are in the position to go ahead and do some actual data science and machine learning using the concepts that we've learned. So let's start off with one of the most interesting aspects of data science, which is plotting. If you're familiar with Python and matplotlib, you would know that matplotlib's syntax is a little wonky. But here we have a very clean syntax and semantics of plotting. So in this video, we are going to take a look at that. What you first want to do is install the plots package, which is essentially the interface to all the plotting in Julia. I've already done that, so I'm not going to run this cell. After that, you need to do using plots, and then you can create some very simple plots using the plot function. When you run this, you will notice that the first time you try to do a plot, it's going to take a little bit of time. The reason for that is Julia does all the compilations necessary to speed it up later on. So the first plot is going to take a little bit of time. So let's go ahead and do that. So you call the plot function. The first parameter is the function that should be plotted. And the second is the range on the x-axis from where it should start. So from -2 pi to 2 pi. So this is the range for which the plot is going to be created for us. So we run that and wait for it to do the pre-compilation and get everything ready. So this is going to take a couple of seconds, and then you see the plot. So as you can see, this looks really clean, very nice plot out of the box, much prettier than the matplotlib's defaults. Now, because this sign is a function, we can also pass it an anonymous function, which can be a lot more complicated. So you can say a function which takes one parameter, which is going to be each individual value for the x-axis, and it's going to plot the sine square x and cos cubed x added together. So you can do any sort of complex function plotting using this syntax. So this looks really nice. Obviously, when you do real world plotting, you're going to be interested in some data, and we'll get to that in the next video. For now, let's take a look at some of the other syntax details. So you can give it the label, you can give it the X label, Y label, and the title. So when you do that, you will see that the label for the negative log function that we are plotting goes in the legend. So minus log X goes over there. Y label is set using the Y label argument, and X label using the X label, right? So this works out really well. So this minus log X is very useful when you do machine learning and classification. So that's why I just wanted to plot this. Okay. So this shows you the details of the plotting library in its basics. Now let's go ahead and plot some specific values. So for instance, we are going to have X go from 1 to 10. So this is our range, and Y values are going to be just 10 random values. Okay, so let's go ahead and do that. So we have Y and X values out. We can go ahead and plot Y1 using plot X comma Y1 comma label is equal to Y1. This is going to do the plot for the values that we have over here. If we want to add another line to this, we can use the bang variant of the plot function. So if you recall, bang means it's going to do some sort of a modification, and the modification is going to be on this plot. So this second plot function with a bang is going to modify the plot by inserting the second series onto it, right? So if this seems too verbose for you, there is an easier way to do this. So you can say plot X, and for Y axis, you can give it a collection of elements, right? So two arrays, each holding the Y values that you want to plot, and you can give them both label, which we are setting as first and second over here. And notice that there is no comma in between, right? So this is kind of a vector. And the reason for that is because typically when you're working with vectors, it's much easier, right? Obviously, Julia is still under development, so this might change, but this is as it stands at the moment. Okay, so we have the same plot over here. We can convert this into a scatter plot by setting the series type as colon scatter. If you recall, this is a symbol, and you don't have to enclose it in double quotes. It works out just as a symbol. Okay, so you do the plot, and this is what it looks like, right? So Y1, Y2. The colors, I am not really fond of the particular values over here, so we can go ahead and change them. So we can change this thickness scaling to 0.7, and we can go ahead and change the opacity to 0.8, and to me it looks a lot cleaner this way. Okay, Finally, we can go ahead and do a lot of plotting. So we can have 4 different series and we can pass them to the plot function, and we can set the palette as dark 2_5, and that gives you this guy over here, right? So depends on which color palette you're interested in. We have a detailed list of palettes over here that you can go check them out. Similarly, on this link, you can go ahead and check all the different attributes that are available for the plot function. There is a lot to unpack over here, but this is the basic and this can get you started. We want to move on to more interesting things, and I encourage you to go ahead and follow these links and explore the different options that are available. In the next video, we are going to take a look at loading some data and then working with that data instead of plotting some random values. Let's go ahead and apply traditional machine learning to a classification problem on an existing dataset. This will just give you an idea of how the built-in libraries for classification work in Julia. So let's go ahead and use the R datasets and ML-based packages. If you don't have them installed, you can install them using these 2 cells. I already do, so I'm going to just start using them. So R datasets provides the information about well-known datasets coming from R, and ML-base is the traditional machine learning collection. So let's go ahead and load the iris dataset, which is the information about different flowers and their species, into our iris field. So there you go. We can go ahead and take a look at what the dataset looks like in this table. That will show up in just a minute. So we have sepal length, sepal width, petal width, and then the species. You might have seen this before as well. Let's go ahead and see what the actual pipeline looks like for doing machine learning on this dataset. So we're first going to convert this into a matrix. So all the rows and only the first 4 columns, which are the features. So those are going to go into X, and the labels are going to come from the 5th column. So there we go. These are the columns that we have. So label map can tell us what the actual values correspond to the actual labels. So 1 is setosa, 2 is versicolor, and 3 is virginica. We can go ahead and use the label encode function to convert all the labels into their corresponding numeric values 1, 2, and 3. Okay. So once we do that, y is going to be converted into these values. Okay, so we are going to now create the training and testing splits. So essentially what we're going to do is we are going to do a per class split, which means for each class we are going to take like 70% values and put them in the training, and the rest of them we are going to put into testing. So the call is going to be like this. So per class split, we are going to give it the y, and we are going to say that 0.7 of the values should go into the trainings. So this is going to return the IDs from the data set, which should be put into the training set. So let's go ahead and do that, and then it'll make sense. So we're going to do using random because we want to have a random sample from the whole data set for our training. What per class split does is it figures out which unique values y has, so 1, 2, and 3. For each of these values, it's going to go ahead and find the values from y where that specific row equals this class. So for each of these class, we are going to do this. Okay. And what are we going to do? We are going to do a random subsequence from these values, and we are only going to pick 70% of those because we'll pass 0.7 to it. Okay. So for class number 1, it's going to pick 70% of the values. For class number 2, it's going to pick 70% of the values, and for class number 3. And all of those row IDs, so these are just the IDs, not the whole rows. So those are going to be pushed into our keep IDs. Okay, let's do that and you'll see what this means. For each of these classes, we are going to get these values. So 2, 3, 4, 6, 7, and all of these. Some of these are going to be from class 1, from class 2, and class 3. The reason we do it like this is, for instance, if you have an imbalanced data set and like 90% of your data comes from one class and we just do a random split, then it's highly unlikely that most of the values are going to come from just one class. So a per class split ensures that we have a good representation of classes in our training and in our testing sets. Okay, so we just get these IDs back. We are going to calculate the test IDs now by calculating the differences of all the values from the training ID. So from 100 to 150, these are the training rows and the rest are going to be the test rows. So that makes sense. Okay. So we have 2, 3, 4 here. So 1, 8, 9 goes over here. Okay. So 8, 9 is not going to be over there, and so on and so forth. So now we have the IDs for training and testing both. Right. So if we do the values. So 103 go here and 47 go here, which is like a 70-30 split. Okay. Then we need another helper function for calculating the actual value. So before looking at this function, let me give you an example. So let's say you have a machine learning algorithm and you put the value in there and it predicts 3.1. Because it's real numbers, it can predict 0.5, it can predict 0.3, it can predict 3.1, it can predict all of those different values. And we can only have the classes 1, 2, and 3. So we need to write a function which, given 3.1, will return either 1, 2, or 3 to us. Okay. This is that function. But before we go into this, just look at what argmin does. So if you say argmin of this list, it's going to calculate the minimum. So the minimum of these values is going to be 0.9, but we're not interested in the actual value 0.9. We are interested in the position of this. So 1, 2, and 3. So if we say argmin, it's going to return 3 to us. Okay. And argmin of, let's say, minus 1.1 is going to be 2. So argmin essentially returns the position corresponding to the minimum. Okay. So once we have this, let's go over here. So we give it a predicted value, let's say 3.1. It's going to calculate the difference from the predicted value and all of these values. And this is going to be distributed. So 3.1 is going to subtract 1. This is going to be 2.1. 3.1 minus 2 is going to be 1.1, and 3.1 minus 3 is going to be 0.9. So once we do an absolute of that, because we're only interested in absolute differences, and then do an argmin, it's going to return either 1, 2, or 3 depending on whatever the closest value is, right? So we do that, and then we say assign class, and if we say 1, it's going to say 1. If we say 1.2, it's going to say 1. If we say 1.7, it's going to now say 2 because it's the closest. So similarly, 2.7 is going to be 3 and 2.2 is going to be 2. Okay. So hope this makes sense. This is because our machine learning algorithms are going to return this value to us and we need to convert this into an actual class, right? So this very simple function does that for us. Now let's go ahead and do the actual usage of classifiers. So first we're going to use the decision trees. So it's very straightforward now. So you're going to do decision trees, and the model is going to be decision tree classifier with a max depth of 2. So if you don't know what a decision tree is, you can look it up and you can study the model, but it's a very powerful model. It's very useful. For us here, it's not important what the decision tree algorithm does and how it works. For us, we are just trying to use it here. Okay. So we create the model and we pass it the values. So fit function is going to do the actual learning, and this is going to be the model that we are using. We are going to give it all the train values and the labels for the train values. So you would remember we had train IDs. So we are going to take all the train ID rows and all the columns from X and the train IDs rows from Y. So that's all there is to it. We do that and we get the result out. So I probably didn't run it here. So train IDs. So yeah, I have a typo here. So train IDs, there you go. So this is now done. And now we can go ahead and do the testing. So we can say Q is equal to the query is equal to test IDs and all the rows. And then we are going to, similarly here, so we are going to do the prediction. So prediction on this model for this query is this over here. Okay. We can find the accuracy, and finding accuracy again is a very simple function. We give it the predicted values and the ground truth values. We are going to check how many of the predicted values equals, piecewise equals, ground truth values and divide by the total number of ground truth values. So that's all our accuracy is, the number of correct answers. Okay. So we can say predictions dt, which we calculated over here. And these are our ground truths. So once we do that, I really should fix this. So once we do that, we get the accuracy of 93.6, which is really good. Decision trees can be combined into random forests, and using that again is very straightforward. So you get a random forest classifier and the number of trees in this classifier is going to be 20. We are going to fit it just as before. So here we go. And we are going to calculate the accuracy for this model as well. There you go, 93.6. Support vector machines are also supported by default. So you can do using libsvm. You calculate the training and testing values. So those go into ytrain and we simply pass them over here. Okay. The reason we're doing this is libsvm requires the structure in a slightly different format, so we have to transpose this, right? So you just have to remember that libsvm is slightly different because it's traditionally done like that. Okay, and we can go ahead and do the learning, and then we can do the accuracy test as well to see how libsvm does on this data set. Okay, so we get 95.74 on libsvm really quickly. So people don't typically do these traditional machine learning models, but if you do want to do that, you can see that the code is very clean, very straightforward. You can work with this. In the next video, we are going to move on to neural networks, and that is where machine learning really shines in Julia, because Julia starts with a very simple concept, and that really explodes into the state of the art machine learning. So in the next video, we're going to do that. In this section of the course, we are going to use Julia to build neural networks from scratch using the machine learning library in Julia, which is called Flux. Now, this is not a course on machine learning, so I'm assuming that you're already a little bit familiar with neural networks and you've worked with other libraries which work with neural networks. If you haven't worked with neural networks before, there are tons of tutorials on the internet. You can look them up and get familiar with them before you start with Julia, because Julia is kind of like advanced machine learning. Okay, it starts from zero, but it comes up to state of the art really quickly. I'm going to give you a crash course on the basic concepts of machine learning, but only the concepts that are relevant to our discussion over here. So to get started, all neural networks are two passes. One is the forward pass, in which you take some attributes of the data that you have, you multiply them with some weights, and you apply some squishing function and you get an output back. Okay, so for instance, you might have w into x plus b is equal to this z value over here, and you can apply a sigmoid or an activation function to it. That is your forward pass. It's fairly straightforward. Then you do a backward pass, in which you calculate the derivative of this loss that you've calculated, or the error that you have, with respect to all the parameters that you have for the model. So the w that you had over here, that needs to change so that when it is multiplied to x, the loss is minimized. And you do that using the derivatives of the loss with respect to w. And then you update it using the gradient descent update function, which is essentially the old value of w or theta. You take that old value, you subtract the derivative with respect to that, multiplied by some learning parameter, which is called alpha. Okay, so these are the three things that you have to do. So let's put them together. So you have the forward pass, which is essentially just a mathematical function. It's not complicated. You have the backward pass, and then you have the parameter updation step. So this is fairly straightforward. This is fairly straightforward. The backward pass is complicated because in this you have to have a very complicated mathematical function, and you have to calculate the derivatives for that. And this is where people struggle with machine learning. You have to calculate derivatives with respect to millions of different parameters, and these are partial derivatives, extremely complicated. So easy, and difficult. The way Julia works is it allows you to specify the forward pass and the updation step, but it takes care of the backward pass, which is the difficult part, automatically for you. And that makes our life very easy as machine learning developers. Okay, so keeping this in mind, let's go ahead and see how Julia does this. So we'll start off with a very basic mathematical function, calculate the derivatives, and then move on to the updation step as well. Okay, so the library is Flux. If you haven't installed it, you can install it using add Flux, and then start with using Flux. So this is our dummy function. So 3x squared plus 2x plus 1, just a basic function which will give you a derivative or gradient of 6x plus 2. But we're not going to calculate this. We're going to get Julia to calculate it for us. So this is our function. And all you have to do is call the built-in function in Flux, which is called gradient, and tell it to calculate the gradient of f with respect to its one parameter, but for the value of x 2. So this is the derivative of f with respect to x when x is equal to 2. That is what this is. The gradient of f with respect to x when x is equal to 2. So 6x plus 2, that is going to be evaluated, right? So 6 into 2 is 12 plus 2 is 4. So we get the right answer over here. Right, so that's all. The gradient part, which was the difficult thing, we did not have to do by hand. So I wrote this here, but we didn't need this. This is just a comment. Okay, we can go ahead and make this a little cleaner because this is in a tuple and we need a value. So we can define a new function df of x. So this df is just for our ease of understanding, it can be any name. So d of fx is equal to this gradient function. We're going to multiply this. So this is the body of the function, right? If you don't remember, recall that this is a function which is defined in a single line. So this is the function name and the parameter, and this is the function body. So what the function body does is it calls the gradient of f with respect to x, so this value, and returns the first element, so 14 back. So you can have this, and then you call df at 2, you get the value 14 back. Okay. So now what df is the derivative of f with respect to x at this particular value. Okay. So this is very easy to work with. Make sure that you understand this. If you don't, go back, run this again, calculate this for different values of x so that you are crystal clear on this, right? So we're going to build on top of this. Now let's go ahead and take a look at functions which have multiple parameters. So for instance, we have a function f which takes two vectors as its input, x and y. Okay. So what the function itself does is it calculates the difference of corresponding elements in x and y and then squares them. Okay. So your typical mean squared error. Okay. This is a simple function definition, nothing complicated going on over here. The only thing is x and y are both going to be vectors. Okay. No problem. Now we are going to take this w as x and b as y. There are two vectors, this and this. We are going to calculate the derivative of f with respect to these two vectors. Okay. And because these are vectors, the derivative is going to be piecewise or partial derivative with respect to this guy separately, and this guy and this guy and this guy. So there are going to be 4 partial derivatives over here. So again, if you don't recall calculus, don't worry about it. Just remember that we are calculating this derivative stuff. Okay. So if you have one w here and another w here, we are going to calculate the derivative of this loss with respect to this w separately and this w separately. So if this was a vector, w1, w2, we are going to calculate derivative with respect to w1 separately and w2 separately. And then, for instance, here q1, q2 separately. So everything is going to be calculated separately, right? Because we need to use those to apply this parameter updation step. Okay. So let's go ahead and do this. So the function is this guy over here. So this is the forward pass, and the backward pass is the calculation of gradient with respect to each different value. So we are going to do that and we get 4 different values. So what this is saying is the gradient or derivative of f with respect to these two values. And because these are vectors, we are going to calculate the derivative of f with respect to w when w1 is equal to 2. So that is this 0. When w2 is equal to 1, and that is this b1 and b2. Okay. So all of these are calculated automatically for us. Now this is slightly difficult to work with. So Flux provides an alternative syntax. So here you have to calculate what w1 is, what w2 is, what b1 is, what b2 is. We have an easier method for doing this. What we can say is we can define a new function gs. This is going to be the body of the function. What this is going to do is it's going to calculate the gradient with respect to these parameters w and b for this function. So the syntax looks slightly convoluted. It's the exact same thing. The gradient with respect to the parameters w and b of this function is going to be calculated, and it's going to be saved in gs. Okay. So when you do that, you get some gradients back. If you say gs.grads, it gives you a huge mess. So it's kind of complicated, but the point of using this syntax is now you can say gs of w and you get 0 and 2. So the same value 0 and 2 back out, you can simply use this to get w1 and this to get w2. Okay. So it works out. Similarly, you can go ahead and get the derivatives with respect to b, which are these guys over here. So same idea, you have a function over here. You need the derivatives, partial derivatives of this with respect to all the parameters. You use this syntax. Okay. When we go ahead with Flux, we are going to get rid of even this stuff over here, and the final syntax is going to be very easy. But we are building this from scratch so that if you have to create your own models later on, you know how to do that. Okay. The final syntax of Flux is very clean, very easy to work with. This is just the building blocks, and that's why it looks slightly messy in the beginning. Okay. Now let's go ahead and create a basic model for Flux. So we are going to create this stuff. We are going to have some x's going in and some weights are going to be multiplied with that. So we have some w's. So these are the random weights. So this is a matrix 2 by 5, and the biases are a vector. Okay. So what is the prediction? You would have seen this before. We multiply weights with x and then add b to it. Okay. So the prediction of x is wx plus b. This is our basic forward pass for a single neuron. Okay. What is the loss? The loss function is y is you do the prediction and then you calculate the squared error and you sum over all the different data points that you have. That is your loss, right? Just a basic loss. By the way, we write this y hat as you write y and then you say slash hat, hit tab, and it's going to convert into y hat. Okay. This looks very similar to the mathematical notation which appears in the paper. So Julia prefers this. So you should get used to doing this. Okay. Anyway, we have the loss function and we have the weights. Now what we want to do is we want to calculate the loss for particular values. So x comma y is going to be rand 5 and rand 2. So this is some dummy data. Our x values are going to be these and our y values are going to be these over here. Okay. So x and y. We can calculate the loss of x and y. So what loss does is we go over there, we predict a y for these x values. So for these guys over here, we predict a y and we calculate what the difference is. Because w was initialized as a random, we are going to get some random loss over here, 3.6. It's not good, obviously. We are going to improve this by applying the backward pass. For that, we need the gradient. So we use this syntax, gradient parameters for this loss function. So the gradient or derivative of this loss function with respect to w and b is going to be needed. Okay, we do that, and because this is very common, we have an alternative syntax as well. So you can use this exact same thing. It does the exact same thing as that. You have a function which is an anonymous function for loss and this guy over here. So this is an alternative syntax. It comes up in Julia's documentation, so it's included over here. But if you understand this is exactly the same thing. Okay. Now we can say gs.grads and you get this big whole mess. But the point is we can say the derivatives for w are gsw. Okay. So this is through slash bar. Now we have the gsw. This is this guy over here. Okay. So the derivative of the loss function with respect to this particular weight, that is in w hat over here or w bar. Okay. We are going to apply this. So this is your alpha. W dot minus is equal to this guy over here. So old value minus alpha into the derivative. We do that. So all the weights are updated. If we calculate the loss now, you will see that the loss has gone down because we have applied the backward pass once. Okay. We can also calculate the derivatives with respect to b. So that is this, and we update the biases as well. And now the loss is going to go further down. Okay. We can go ahead and do another pass by calculating the derivatives with respect to w and b again. So we're going to do this. And if you do this now, it's going to update, and you update this and you calculate the loss, it goes further down. You calculate the derivatives with respect to b, update your b, and you calculate the loss, it goes further down. Right? So our pass is going to be calculate the gradient with the new w and b values and update those, and that's your basic neural network iteration. Calculate the derivative with respect to current values of weights and update the weights. That is the thing. Let's go ahead and revise this whole thing again. It's very dense, so you might have to look at this again and again, but this forms the building block of the Flux library. And as you can see, if you get rid of everything, it's just 3 or 4 lines of code, right? So let's go ahead and take a look at this. So these are our random weights and biases. We initialize them randomly. Our forward pass is simply the multiplication of x with w and then addition. Our loss is just the mean squared error, which we normally have. X and y are going to be some dummy data. So some dummy 5 values for x and dummy 2 values for y. Okay, these are the values. First we look at what the loss is, then we calculate the derivative with respect to the loss, and then we update the weights first and then the biases. That's all there is to it. So going back to the figure, we do the forward pass, we calculate the derivative, and we update the weights based on the derivative that we've calculated. We do this again and again, and it becomes very clean. So let's go ahead and put this in one cell so that you understand what's happened. So we have the weights. So there you go. I'm going to do this in real time so that you can see. So these are our weights and biases. Our predict function is this. Then we have our loss function. This would be our loss function. Then we need the gradients. You can use either of these two. Okay. So let's go ahead and put these in a separate cell. We take our data as well. So our data is going to be this. Let's put this over here. So I'm putting everything that has to be repeated here and everything that is done once over here. Okay. Finally, we have the weights over here, and we are going to update the weights using this. Similarly, for biases, we have the calculation of biases and updation as well. Okay. And then we output the loss with respect to X and Y. Okay. So hopefully this makes sense. Let's go ahead and output the loss initially as well. So there you go. This is our initial loss. Now let's go ahead and do the iteration. Loss goes down, you do it again, and loss goes further down, and you keep doing that, and loss is going to keep going down. Okay. Hope you understand this. Forward pass, backward pass, and the updation. So that's all there is to it. This is all you need to write a simple neural network in Julia. If you've done this stuff with any other library, you would notice that this is extremely easy, much easier to work with than any other library. So in the next video, we are going to take these basic concepts and build a multi-level neural network instead of a single neuron. In the next couple of videos, we're going to talk about generative adversarial networks, but the name isn't important. We need to first look at what the issue is that we're trying to solve. So here's the issue. In general, whenever you're trying to collect data from the real world, it would be easy to get unlabeled data, but difficult to get labeled data because labeling requires human effort. On the flip side, large neural networks need huge amounts of data to train. So we have a problem over here. Finding labeled data is difficult, but we need large amounts of data to do proper training. So the issue is, can we find a way to train neural networks with very little labeled data? So we're going to start off with some unlabeled data. So for instance, you have some images downloaded off of the internet. You don't know what the images are of, but you have a large collection of them. As you can imagine, getting unlabeled data is fairly straightforward. And what we're going to do is come up with a way to learn the structure, the internal structure of the data without labels. But the problem is neural networks require a loss to operate, gradient descent and all that. You've seen all of that. Where is the loss going to come from if you don't have labels? So here's what we're going to do. We are going to set up a pipeline in a very specific manner. And that is what the generative adversarial network is going to be. So let's start off with an example, and we'll try to explain visually what this generative adversarial network or GAN is. So here's the typical example given for the explanation of GANs. Imagine that you have a bank teller and they're sitting at their bank, and a person comes in and tries to give them a $20 bill or note, depending on which part of the world you're from. So they give them this $20 note, and the bank teller says, this is a fake. This doesn't look like a real one because it doesn't have the proper features that a proper real note has. Right? So a fake is identified by the bank teller very easily because it's a very obvious fake. Okay. But if a proper, real, genuine note is presented to the bank teller, they say it's a real. So we have this bank teller who is acting as a neural network, as a discriminator, which discriminates between real and fake notes. If you give it a fake, it says fake. If you give it a real, it says real. But it can make mistakes. If the fake is really good, it can make mistakes. So that is where this part comes in. So this portion over here is going to be a neural network. It can be as complicated as you want it to be, but for now we're going to keep it as a simple feed-forward network. Continuing on with our story, if a person comes in, presents a fake note to the bank teller or the discriminator, the bank teller is going to say it's a fake, but it's also going to tell the counterfeiter that the note is fake because the colors are off, for instance. Whatever feature is used to identify the note as being fake is going to be communicated to the counterfeiter.
Using this information, the counterfeiter is going to produce better fakes the next time around, but they're going to make another mistake and that is going to be communicated to them. So slowly and gradually, the fakes are going to get better and better and better. And the discriminator is going to have difficulty identifying the fake from the real. The problem we have is, where does this fake come from? How are we going to generate this fake, and how are we going to learn from the information that is given to us? But for now, understand that this portion over here is called the discriminator. It only does one thing. Given some note, it decides whether it is coming from the real portion or the fake portion. Let's translate this to a machine learning model that we understand a little better. So MNIST. For instance, we are going to have some real MNIST digits going into the discriminator. It should call them real. It should label them as real. And if you generate some noise, some random pixels, and feed them to the discriminator should say fake. How is it going to learn? It's going to learn using these simple labels of real or fake. When we feed it a real, we're going to tell it real as the label. And when we feed it a fake, we're going to put fake as the label. So even though the data itself is unlabeled, we don't know that this is a 4. We just know that it's a real world image of a digit. That's it. It doesn't have to be labeled. Even though we have labels in MNIST, we're not going to use them. We are simply going to use the images. As far as we're concerned, it's unlabeled data. Okay? So that is the discriminator part. The other part of a GAN is this part, which is going to generate some fakes. So we're going to have a generator over here and a discriminator over here. And these are going to act as opposing entities in our whole network. Okay, so let's take a look at that very briefly as well. So here's how our generator is going to work. We are going to take a vector. It's going to have some random noise over here. We'll explain why this is in just a minute. We're going to feed it to our generated neural network. It's going to be another neural network. It can again be as complicated as you want, but for now it's just a feed-forward network. The only requirement is that the final output of this neural network has to be a 28 by 28 pixel image, which is the same size as our real data. So the size has to be the same. The actual values within the pixels can be anything. It depends on what the values of the weights in the generator are. As you can imagine, when we start and initialize all the weights as random, we are going to get all of these multiplications and the output is going to be some random noise. That random noise is going to be fed to the discriminator, and the discriminator, I say it's a fake because it's an obvious fake. So that is how our whole architecture is going to work. But how are we going to do actual learning? So we feed some real data and some fake data to the discriminator, and the labels are real or fake. Once we do some training based on these, we are going to get some gradient or loss back out, which is going to train the discriminator weights. So all of these weights are going to be updated so that the discriminator is better able to differentiate between real and fake images, right? So this is where your understanding of deep learning comes in. You understand that given this real data or fake data, the weights are going to be arranged in a way that the discriminator should be able to correctly identify the image as being real or fake. And here's the central idea behind a GAN, or a generative adversarial network. If the discriminator can identify real data from fake data, that means it has somehow internally recognized what real data, quote unquote, real data means. What is it that makes some data real? So it's learning some internal representation even without any labels. So that is the power of the discriminator over here. What about the generator? The generator is also going to be trained whenever the discriminator makes a correct decision. Whenever we give it a fake and it is identified correctly as fake, we're going to get a loss back out, and that is going to be propagated to the generator so that the generator also makes better images in the future. So this is how this whole thing works. We can give some random input to the generator, and by changing this input, we can have the same generator generate different types of images out over here, right? So we change the latent vector. This is called the latent vector because it's hidden. We don't know what these things mean, but they are going to have some effect on the output over here. So we give some value to the generator generates some image that is fed to the discriminator, and the discriminator, if it says fake, the generator is going to learn. If it says real, the discriminator is going to learn. So both of these learn, and the idea is that they are acting in opposition of each other. The generator is trying to make sure that the discriminator identifies this thing as real, and it's the discriminator's goal to correctly identify real as real and fake as fake. So because they are both based on networks and they are working as adversaries, as opposing parties, and this portion over here is generating images out of thin air. Therefore, we call these generative adversarial networks, or GANs for short. So how does this whole thing works? It almost magically works like this, that generator is slowly going to learn how to generate real data. So once you have both the discriminator and the generator trained, you can throw away the generator, and the discriminator now is able to identify some internal structure of this real data. Now you can go ahead and use this discriminator as a pre-trained network and do some fine-tuning or transfer learning and all of that. On the other hand, you can use the generator to actually generate data which looks like your real world data, even if you don't have that real world data. So we can augment the MNIST data by generating more digits out of thin air. And in the next few videos, we are going to take a look at how we can use Julia to actually code generators very easily and generate MNIST-like images out of thin air. So let's do that in the next videos.